So in this video, we are going to pick up where we left off in the last one. We have set up this idea of a transmission line with a moving current wave across it. And we're going to use our knowledge of the fields that are within that transmission line, along with Maxwell's equations, to try to work our way toward figuring out what the voltage is. And so let's go back to our diagram here. All right, we have a current defined as follows: I0 times cosine of omega t minus beta z. That's our definition of a positive z moving wave of current. And so let's do this in a few steps. We're going to work our way toward figuring out what the voltage is. So step one is you want to determine the magnetic field between the plates. Right? So let's calculate the magnetic field between the plates. And for this, we are going to use a result that we figured out earlier. And that was the result for a sheet of current on a plane where you've got current moving in one direction. If you have a sheet of current moving in one direction, the magnetic field is parallel to the surface of the plate, but perpendicular to the surface, to the current itself. In other words, in this diagram, if I just take one of these plates, the magnetic field generated by this current I is going to be in the x direction. Again, parallel to the plate, but perpendicular to the current. And the magnitude of that current is going to work out to be the following. It's H equals plus or minus Js over 2. And in this case, it's going to be in the x direction. All right. The plus or minus is simply asking the question of which side of the plate are you on. Since you basically have a difference of Js from one side of the plate to the other, so it's basically half in each direction. That's basically generated by one of these plates. Right? So this is from one plate. All right, now let's make a little substitution right here, because Js, we know what that is. That's going to be the current I divided by A, the width of the plates. That's going to give us the current density, the surface current density, and we know it's going to be pointed in the z direction. All right. In this case, this Js is just a magnitude. So this H, we're going to rewrite this as I over 2A in the x direction, and that's a plus or minus, because this again is a absolute value right here. All right. Now this is again the magnetic field from one plate. So let's look now at what is the magnetic field way above these plates. Above these plates, we're basically going to have a magnetic field of I over 2A from one plate, and for the other plate, it's going to be a negative I over 2A, which means they're going to cancel. You'll notice that the formula for magnetic field from one plate does not depend on distance. That's true as long as the plates are sufficiently big, almost infinitely long in extent. If that's the case, then these two plates have equal and opposite currents, which means that above both plates, they cancel out. And so we're going to have a magnetic field of 0 above the plate. You can make the same argument for the magnetic field below the plate, that H equals 0. In between the plates, however, those magnetic fields are going to add up, which means that in between the plate, we're going to have an H of twice this I over 2A, which means it's I over A in the x direction. And now let's substitute our definition of what I is. This is an I0 times cosine of omega t minus beta z. And this is in the x direction. Right? So that's our answer to step one. I want to remind you that it was Maxwell's equations that originally gave us this idea that H equals plus or minus Js over 2. It emerges from Ampere's law that the curl of H equals J. And that was derived earlier, so I'm not going to redo it here. But we have used basically this fourth Maxwell's equations in order to figure out the magnetic field generated from this current. All right, so that's step one. Step two is we're going to take the time derivative of the magnetic flux density. And what we're going to do is we've effectively used the fourth equation right here. All right, so I'm going to put a little check mark there because we've used it. Next equation we're going to use is the top right one, that the curl of E equals minus dB dt. And we've got H, and so from that we can get what B field is, because B equals mu, the permeability, times H. And so from that we can get that B, and this is now step 2, equals mu times I0 over A times cosine of omega t minus beta z in the x direction. All right, now using this third equation over here, we're going to take the time derivative of dB dt in order to work our way toward getting what the electric field is. All right, so let's take dB dt. dB dt, I'm just going to take the derivative of this. The mu times I0 over A stays the same. The derivative of a cosine is a minus sign, so let's put a minus right here and make that a sine of omega t minus beta z. And because we're also taking the derivative of what's inside the sign, we have to pull out an omega from this sine function right here and make that x hat. Now to reproduce this Maxwell's equation right here, there's a minus sign, so I'm just going to add a minus sign on the left, and I'm going to convert this to a plus sign. All right, so here we've basically got an expression that tells us what the time derivative of the magnetic flux density is. And the next thing we're going to do is try to work with that and try to work our way toward the electric field. Right now, from this top right equation, we can see that if we have the negative time derivative of the magnetic flux density, we know that equals to the curl of E. So let's write that down. That's going to be step 3. Is relate to E via curl of E equals negative dB dt. All right, so I'm going to write down this whole expansion of the curl of E. It's going to be x, y, and z, d dx, d dy, d dz, ex, ey, ez equals negative dB dt. Now in this case, dB dt only has an x component, so that's the only component that's going to be interesting to us. So let's focus only on that piece of the curl of E. And from that, we're going to figure out that x hat times dez dy minus dey dz equals negative dbx dt, right? Where this portion right here is negative dbx dt. So we can substitute that in. Now let's simplify this a little bit further. Now that we have this x term right there, we can get rid of that because we're only focusing on the x component of this equation. But let's take a look at this dez dy minus dey dz. At this point, we're going to invoke a bit of a symmetry argument, because if we take a look at this right here, there ought to be no electric field in the z component, right? There ought to be no variation in the y direction. And so for that reason, because dez can be assumed to be 0, right? And the reason we can assume dez to be 0 is that we know that electric fields cannot exist parallel to conductors, right? These two conductors are both metallic, and so they're perfect conductors. And so any electric field that exists right at the boundary of this electric field, of this electric plate, has to be perpendicular to it. In order to know that, by the way, we get that from Gauss's law, right? Gauss's law is what told us that only electric fields can exist perpendicular to perfect conductors. They can't exist parallel. So we've now used this first equation right here in addition to the second. So you can see we've now used 3 of the 4 Maxwell's equations, and we're almost there. But the upshot is that we can get rid of this term right here, because we know that EZ equals 0. There can't be an electric field that is parallel to the plate. There can only exist an electric field that's in the y direction between the plates. All right? So let's expand this out. And from this, we can get that negative dEy dz, bringing this up here. And let's substitute the full minus dBx dt, which is over here. And so this equals omega times mu times I0 over A times the sine of omega t minus beta z. All right? So we are almost there. You can see we are very close to being able to actually figure out what the electric field is. And so step 4 is to calculate the voltage between the plates. In order to do that, let's first take this equation and integrate it with respect to z in order to get the electric field. In other words, that the electric field in the y direction is going to be the integral of dEy dz with respect to z, right? That makes sense. So let's take this formula right here and let's integrate it with respect to z. And it works out to be the following. Ey equals mu times I0 times omega divided by A. And the sine becomes a cosine, right? So there's a cosine of omega t minus beta z. I'm going to put a minus sign here because the integral of a sine is a negative cosine. Right now, there's one more missing piece, which is because the inner part of this cosine has a z dependence on it. We also have to integrate this argument inside the cosine with respect to z. And that's going to end up pulling out a minus beta. And so that minus is going to turn us into a plus, and we're going to have to put a beta in the denominator. All right, so with that, we now have our electric field. It only has a y component, and it's characterized precisely with this cosine times this junk that's starting out. Right now, we're almost there. Step 4 will be completed if we can figure out what is the voltage change between the plates. And that is relatively straightforward, because the voltage is going to be the integral from the bottom plate to the top plate of the electric field dotted with ds. In which case, the electric field we have defined, and ds is going to be a small length dy in the y direction, because we are basically taking a path that starts on the bottom plate and works its way up in the y direction until it reaches the top plate. All right, if we substitute all that in, this turns out to be that this dot product will only pick out the y component of E. So this is going to be mu integral from 0 to d of mu times I0 times omega divided by A beta times cosine of omega t minus beta z dy. Now, because everything in the integrand is constant with respect to y, there's no y dependence, this integral is actually extraordinarily simple to do. We can just get rid of the dy in the integral and multiply it by d. All right, this is the integral of a constant. And so let's throw in a d right there. So here we have it. We've got the voltage in between the plates. And all we needed was Maxwell's equations to help us get from the voltage to the current. Right, but now that we're there, let me remind you of what our definition of the current was. Right, the current was I0 times the cosine of omega t minus beta z. Right, that equals the current. So let's now ask the question, what is the what is the impedance of this transmission line, right? Z0 equals voltage divided by current. If you plug this in and divide it out, you are going to get the following. You're going to get that V over I equals mu0 times omega times D over A times beta. And you can simplify this a little further. This turns out to be the square root of mu over epsilon times D over A, right? This works out to be the transmission line impedance. If you want to see how I made that link, I'll just remind you that beta equals omega over the propagation velocity, and the propagation velocity equals 1 over the square root of mu times epsilon. So with that, you can actually simplify this, and you end up with this mu over epsilon times D over A. Now here's the neat part. All right, let's complete this picture. And we're now ready to recall this from the textbook, figure 2.8. Here's a parallel plate transmission line, and take a look at that formula for Z0. Right, Z0 equals D over W times the square root of mu over epsilon. Exactly what we just derived with Maxwell's equations, right? So the lesson here is, as I've been saying so many times, the parallel plate transmission line is not so much a guide of voltages and currents as much as it is a guide of electric fields and magnetic fields, which create each other via Maxwell's equations. And it's the boundary conditions that simply allow those to be manifested as voltages and currents between and along the two plates. All right, so with that, we can conclude, and we have now completed this link, and we've now understood that inside of that transmission line, there was all along a radio wave. In the next lecture, what we are going to do is remove the transmission line entirely. And even though we still don't have the transmission lines, we can still have electric fields and magnetic fields. And it stands to reason that those magnetic fields and electric fields will propagate as a wave even in the absence of a transmission line. If you don't believe me, we're going to see that in the next lecture, and we'll finally have graduated, and we will finally have recognized exactly how a radio wave works. So stay tuned for the next lecture.